Good morning, friends. We are seeing design of one-way slab, design of cantilever slab. Now we'll start with design of two-way slab. In the same line with one-way slab, two-way slab, we have to design a two-way slab. In the same line of one-way slab, cantilever slab, we have to design a two-way slab. So only difference is that in one-way slab, the main steel is provided along one direction and this main steel is provided along shorter span while distribution steel is provided along longer span. In one-way slab, the main steel is provided below the distribution steel while in cantilever slab, the main steel is provided above the distribution steel. But for a two-way slab, since it is a two-way slab, the main steel is provided along both the direction, that is along x direction and along y direction in a two-way slab. Then as per design steps, we'll start with step number 1. In step number 1, we have to calculate the depth required. You can start with just like one-way slab or cantilever slab, but you can use another formulas like this, that is overall depth for two-way slab is calculated, that is capital D is equal to Lx upon 35 for Fe250 and D is equal to overall depth, D is equal to Lx upon 0.8 into 35 for Fe415. Rather than this, if shorter span Lx is greater than 3.5 meter and live load is greater than 3 kilonewton per meter square, D is equal to, that is this D assumed, this effective depth assumed is Lx upon 20 into mm, and assuming cover, find the overall depth, and these are the assumed overall depth. So you can start with these formulas or directly you can start like this, Lx upon 20 into mm. Here Lx is considered not Ly because Ly is the longer span and Lx is the shorter span. While designing, you have to always consider the main steel span, that is Lx. Lx is the shorter span and main steel is always provided along the shorter span. So you have to consider the shorter span. Then step 2, calculate effective span. That L effective is given by shorter span length, that is Lx, plus the distance between support whichever is less, that is the L effective. Then in step 3, calculate the loads, that is self weight of slab, weight of finishing, live load. These loads are given in the problem and the total of this load is taken as a total load, and then convert this total load into factored load by applying the factor of safety as 1.5. Then in step number 4, you have to calculate the factored moments. Since in two-way slab, the main steel is provided along both the directions, that is along x direction and along y direction. So we have to calculate the moments along both the directions, that is along x direction and along y direction. So to calculate the moment along x direction, use the formula alpha x into factored load into Lx square. That is this alpha x and alpha y, these are the bending moment coefficients and these are taken by Ly by Lx ratio. If Ly by Lx ratio is 1, then alpha x is 0.062 and alpha y 0.062. If Ly upon Lx ratio is 1.1, then alpha x is taken as 0.074, alpha y 0.061. This table is given in the problem or directly alpha x or alpha y values are given in the problem. By putting these values of alpha x and alpha y, we have calculated this factored load, and we know the effective span along x direction. You can calculate the bending moment along x direction and bending moment along y direction. So calculate absolute maximum bending moment out of above. So from calculation of these values, you consider the maximum value of bending moment for further calculations. Now step number 5, to determine required depth for bending moment using equation, that is MD is equal to 0.149 FCKBD square for Fe250. These values are we have used in one-way slab, in cantilever slab. Again we are going to use in two-way slab. That is MD 0.13, that is limiting moment. These are the limiting values of bending moment. That is MD 0.138 FCKBD square for Fe415, 0.133 FCKBD square for Fe500, and check D required. If D required is less than D assumed, if not, increase the value of D assumed. See here, if D required is less than D assumed, if not, increase the value of D assumed. This is very important. The next, step 6, to determine the steel area. Since we have calculated the bending moment along both the directions, you have to calculate the steel along both the directions, that is steel along x direction and steel along y direction. So area of steel in x direction, considering bending moment along x direction, by the using equation MD is equal to 0.87 FYAST into bracket D minus 0.42 XU, where XU, this is the neutral axis formula, but using this formula you can use the directly the formula for calculation of steel in one way or cantilever slab, and that formula is AST main is 0.5 FCK upon Fy into bracket 1 minus under root of 1 minus 4.6 MD upon FCK BD square bracket complete B into D. This formula you can use for calculation of main steel. Only the change is in bending moment. When you are going to calculate the steel along x direction, take the bending moment along x direction, and when you are going to calculate the steel along y direction, take the MD along y direction, and the depth, that is FCK BD square bracket complete B into D, only the depth changes, overall effective depth changes. That change we will see while solving the problems. The next step is to find the spacing. Same formula is adopted to calculate the spacing, that is spacing along x direction, spacing along y direction, as width into area of one steel bar divided by total area of steel. Then check for deflection. This check normally not required for one-way slab, but for two-way slab, if in the problem it is asked to check for deflection, you have to check the deflection criteria also. So while solving the problem we can see all these things. Then check for shear. There is no need to check the slab for shear, as shear force is very less. Further, it is difficult to provide shear reinforcement for slab having thickness less than 200 mm. So shear check is not required for one-way, two-way slabs. These are the bending moment coefficients. Okay, thank you.